So next we have number 3. Prove that the greatest integer function f, so they are calling it f, which you know what it is. It maps the set of real numbers into itself, and given by this is neither 1 1 nor 1 2. This given by this part looks stupid because it does not really define the function. Instead, it just shows that this is the more common notation we use to denote this function. But we already know what the definition of the function is. So we have to prove that it's neither 1 1 nor 1 2. So let's do it. So we start the solution by again defining what this greatest integer function actually is, because it's not given there. So I think it's a good idea to define it here. We know that for any real number x, f of x, which is this thing, denotes the greatest integer that is less than or equal to x. So now if you evaluate f of 0, for example, what are the integers that are less than or equal to 0? All the negative integers are less than 0, and 0 itself is less than or equal to 0 because it's equal to itself. Among all these integers, minus 3, minus 2, minus 1 and all the other negatives and 0, what is the largest? 0. So that is why f of 0 is 0. What are the integers that are less than or equal to 1 over 2? Equal to, that's not possible because this itself is not an integer. If you think of the real number 1 divided by 2 or 0.5, the integers that are less than it are again 0, minus 1, minus 2 and so on. So in this case also the greatest is 0. If you find it a little difficult to understand what this function gives you, think of the number line. You locate your input x on the number line, and then you see those integers that lie on the left side of x. There will be a greatest one among them, that is the greatest integer function value. That's it. So you see that f maps two different inputs onto the same output. So obviously it's not 1 1. And next, how is it that f is not onto? To show that f is not onto, we notice this fact. We concentrate on the fact that the output of the function, outputs I should say, because there is not a single output, the outputs of the function f are all integers, because that is the definition. The greatest integer less than or equal to x. The input x may not be an integer. In fact, it may not even be a rational number, but the output is always an integer. So if you choose a non-integral point from the codomain, for example 1 divided by 2, that can never appear as the output for any input under the function f. But then that means that f is not onto. So there we have the solution. So in this next one we have the modulus function, and that stupidity can still be seen here. This is also a function from R into R given by this. What does this tell you? Nothing. What is the meaning of this symbol? You already know what it means, that this symbol is equal to x for a given value of x. This symbol is x if x is non-negative. But if x is negative, then the symbol means minus x. But if we already know the meaning, then what is the point of writing like this? And if we don't know the meaning, then this also is meaningless. You can just simply say, show that the modulus function f, just give it a name and that's it. We already know the modulus function has already been defined in the text, and then straight away you ask for this. But of course, the people who wrote these books, they like to write essays. That's why they are presenting things like this in an extremely hilarious manner. But anyway, let's see how it is neither 1 1 nor 1 2. So lack of one-to-oneness can be seen like this. Because we are dealing with the modulus function, which we know always gives us non-negative real number outputs. So we can use that fact and evaluate the function at the 2 points -1 and 1, and in both the cases we are going to get 1 from the definition of the function. So that's why the function is not 1 1, because different inputs are giving us the same output. And again we can use this same fact that all the outputs are non-negative to also show that the function is not onto, because negative numbers are there in the codomain, but none of them will appear as the image of any input under the function. For example, there is no x in R for which f of x is equal to -1. So that's why the function is not onto. Next we have the signum function. Now this looks okay because the definition is given here itself. We have to prove that this one is also just like the previous two, neither 1 1 nor onto. And what is the function? Let's see. When our input is negative, the output is constantly -1. If the input is positive, the output is constantly 1, and if the input is 0, then the output is also 0. So our function f is not 1 1 because of this. For example, f of 1 is 1 and f of 2 is also 1, although 1 and 2 are different inputs. That is because whenever the input is positive, the output is constantly 1. And our function is not onto. That is because the codomain is large. It is the entire set of real numbers, but the actual distinct outputs this function has are simply -1, 0 and 1. So you choose any real number other than these 3 that is not going to be appearing as an output for any input under the function. For example, there is no x for which f of x is equal to 1 divided by 2, although this real number is here in the codomain of the function. So that is why the function is not onto. And let me just end this video here. There are other exercises after this which we will solve next week. So see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.